Okay. These words are due to Kolmogorov, and we can say that it's also a theorem. So it says that behind every theorem lies an inequality, and if you want to show any theorem, so you have to look behind it and find the inequality to prove. Okay, there is two kinds of inequalities in Riesz space. You can have an inequality which is true in the classical case, and you want to get a generalization, but sometimes you don't have an inequality, and you have to discover the inequality, which can be very simple in the classical case, but it's very useful in the Riesz space. For example, the inequality for used many times by Dr. Usman and other mathematicians, that if you have x minus x of n(e) less or equal than x2 by n, if you work in some algebra structure and E is a unit. Okay, I'm not good at this. The same problem, no? Okay, these two ideas that they work. So for tools and technicals used to prove inequality, we can use convexity. So we translate convexity from the context of real analysis or standard analysis to Riesz space. I will show some results on this direction. We can use functional calculus to return to the classical case. Some ideas coming from measure theory and probability theory, or also matrix theory and matrix positive theory. And so, okay, just here a list of inequality proved in the generalized to the setting of Riesz space. You have the Chebyshev inequality, which is more general than Cauchy-Schwarz inequality. The Chebyshev inequality, Holder inequality, Cauchy-Schwarz, Minkowski, Jensen, Burkholder, and the Upcrossing inequality for martingales. Martingales has been generalized in the setting of Riesz spaces, and a lot of theory from the probability theory are translated to the setting of vector lattices. For example, just a pedagogic remark about the Minkowski inequality. In almost all standard books, we find these three inequality in order. So it's Young inequality, then Holder inequality, and after Holder we prove Minkowski inequality. But which seems not natural, because when we want to show that this is a norm, we need the triangle inequality, and so we do all this. In fact, there is a direct proof which is not very known and can offer ideas in this space, just to use the convexity of the function Tp. So this is the idea. So the Minkowski inequality in Riesz space has been proved first by Grobler, and Grobler follows this idea. So he shows first Holder inequality and then Minkowski inequality. But you can, for x and y, you can divide by this. We use the notation of norm, although it's not proven it's a norm, but this is equal exactly this. Here you have y divided by, and then you put this power p. Now you use, this is the sum of this term is equal to 1. So you use convexity and you integrate. So you get the Minkowski inequality. If you want to use this proof in the Riesz space, in Riesz space we have a condition expectation T, which replaces the integral, and the formula is, the norm is given by this formula. So we need to prove some result on convexity, use the convexity, and here there is some problem by if we divide by some terms in the Riesz space. So we look to the local inverse, something like that. So we can obtain a very quick proof. It's simpler than the proof given by Grobler, and another proof that I proved with a colleague, Majdi Trabalsi. So this is easier, even in Riesz space. So we stop here. Okay, so in context of Riesz space, you can stay here. I mean, we work in this Riesz conditional triple. It's introduced by several people here, by Watson and Marwa. E is a didicant complete Riesz space. Small e is a weak unit, and T is a conditional expectation. So the conditional expectation plays the role of expectation and not the conditional expectation in classical case. Okay, we have the definition of LP space. So we need function calculus to define LP. So for the power of P and for this power, and there is a developed work by Grobler about function calculus and using Daniel integral and the notion of subcompletion to give a satisfactory development. It's easy to deal with. So, and we can define a vector valued norm. So as Bruce has remarked, the range is an F algebra and the range of T, and maybe the talk of Kisraev gives us ideas to get more applications. This is Burkholder inequality, and this is proved first by Grobler, and Grobler uses representation as a C of K space. So with K is compact, extremely disconnected. Then he proves the result in this case and return to the space himself. Sometimes it is not easy to use this kind of function because it's not, the inequality did not concern element, but also there is some operators and it's not easy. This is Minkowski inequality. Now we have several proof. This the idea following this proof in classical case is not yet published, and we need some generalization of convexity, because as Riesz space has an order, so it's easy to speak about convexity because the convexity is this inequality. And this inequality work in Riesz space. So we can speak about convex function from a Riesz space to another. And but sometimes we need more general notion. So we think of replacing this T by something other. So here we can define the kind of convexity by taking T an element of the Riesz space. So such the sum of T and this will be E minus T. So T is an element in the interval 0 E. Okay, in the martingale theory, we can develop a martingale theory using a conditional expectation. So filtration is a sequence of subspaces, or which can be defined through a sequence of conditional expectation. And we have an algebraic understanding of the notion. So it seems to be easier. So we have this formula for the conditional expectation. This is the amphibum. And then we can define the sequence of conditional expectation with increasing rows. And the property of martingale can be written like this. So this is the conditional expectation given Fn. So this is the condition. And it seems to be easier. And we can use the algebraic property, not on general used by probabilist men working on the theory. So the Upcrossing version in Riesz space has been proved first, I think, by Bruce and Labuschagne. Then Grobler gave another version. And when she? Okay. Okay. Then Grobler gave another point of view using bounds and upcrossing and then another thing of another point of view. So in the classical case, we have two value, and this is how the process behave, and we count the number of upcrossing. Here there is an upcrossing, then we can get another, etc. And it's difficult to get a satisfactory generalization of notion. So as Bruce knows, some notions take many times to be formulated in the Riesz space, and we can state many statements and test them and discover that they are not suitable. So I want to say some words about this Upcrossing theorem, that in the classical case, it's a sequence of random variable. The process is sequence, and we can take a continuous version, but continuous, the parameter lives in R plus or in R. But there is another version with nets. So in classical case, normally we have the Radon-Nikodym theorem. So we prove the existence of conditional expectation, then we prove martingale, and then we prove some convergence result on martingale. But I don't know the date exactly, but we can say recently, not exact information, there is a generalization of martingale indexed by net, and then we can speak without mentioning the conditional expectation, we can define martingales before the conditional expectation. And then we prove some result on martingale, and then we prove Radon-Nikodym theorem as an application of martingale theory. So with one of my colleagues, we want to generalize this approach in Riesz space. And because there is a difficult proof of Radon-Nikodym theorem in Riesz space, and the proof by martingales is very elegant, and as all people like elegant proofs, so it's very elegant. I can't say it's simple, but it's shorter, and yeah, it's very nice. So I like the proof very much, and I want to produce Riesz space version of this. So we can introduce martingale, but to prove the most important result, the Doob convergence theorem on martingale, in the classical case, they prove this for sequences. Okay, it's proved for sequences by people before, so by Bruce and Q and Labouchagne. But if we assume that it doesn't converge for nets, then we can return to sequence, and this part cannot happen for the Riesz case, as Bruce explained. For the completeness is easy for classical case, but if we want to produce a proof similar, so it doesn't work. And our challenge is to prove an upcrossing theorem for general case in the Riesz space. And we tried several times. Sometimes we thought that we proved it, we are happy, but next we discover a mistake. And until now, it's not known, so it's a problem. Could we have an upcrossing theorem for martingales in Riesz space indexed by a net? Okay. This approach in classical Riesz space is very nice because we can prove some classical result as Lebesgue theorem for derivative by martingale's tools. So this idea is very nice. So okay, but I have to move to the next page. I don't know. What's the secret? This next page. Okay, this is a Doob inequality for Riesz space, obtained essentially by Grobler. And the proofs are not very easy, so we are led to develop more result and more ideas to get this generalization. I'll speak about a very famous inequality by Burkholder. It's okay. For example, in one of the paper of Grobler, he used some version of Fibonacci theorem. It seems that he used a version of Fibonacci theorem, but it seems that the result is okay. The result is true, but there is no result on Fibonacci theorem. So this motivates us to develop some theory or Riemann integration on Riesz space and proved this formula used by Grobler. Now, some words about convexity. So we can give the same definition of convexity in Riesz space. And here I will give a result which can help us to give another proof of Minkowski inequality. Also, to generalize the theorem, we have several tries, and finally we get the correct version. So, for example, this function, this is positively homogeneous. So there is some theorem of convex function for positive homogeneous function. So I guess it's wanted. You can stay here. My talk is a little short, so for this reason, I mean, do this to make it to be in time. So, for example, if we think of the Minkowski inequality, we want to show this inequality. Okay, so this sub-additive, but it doesn't work. Okay, it's you. Okay, we can introduce this level set, and we have this theorem for convex function on subset of Rn. For homogeneous positive function, convexity is equivalent to be sub-additive. Okay. And we want to get a generalization for Riesz space. So the statement may be this. This one should be okay. So if we arrive in R, so we changed just the domain by some convex subset of Riesz space, it's okay. But what we want to prove that most of our inequality, our function takes value in a Riesz space and not in R. So we need another theorem. And this generalization of these two theorems, so the first one is a connection between convexity and sub-additivity for homogeneous, positive homogeneous function. And the second is a connection between convexity and the convexity of the level set. These are true in classical case, and we want to prove that they are true in Riesz space. The first one is true, but the second is false. And when we look at this theorem, we want to use it to prove Minkowski inequality. So we need both of them. And then we think of another generalization. This is the statement. So so we replace the level statement, which is just one set in the classical case, the set LF1 by LFU or LFA for every positive A, for all A. And this theorem works in Riesz space. And now, as application, we can use it to prove, for example, Minkowski inequality. What does happen? Okay, next. It doesn't work. Next. This is the next. Okay, this is a very useful result. If you have a convex function in real case, and by function calculus, we have this function in a Riesz space. So the function still convex in the Riesz space. And then, for example, this function is convex for p more or equal than 1. So this function, as a by using function calculus, is also convex in the Riesz space. The function x, the logarithm of x, if it is well defined, of course, it's concave and also in the classical case. So we can use it. Next. Okay. This is the Burkholder inequality. So Burkholder inequality is a very deep inequality in classical probability. And if we have a process which is an L2 to define this quadratic variation, and also in LP to define the norm P, then we have this inequality. And as application, we can prove several results, among them the convergence of, I will mention a result using Burkholder inequality. So here, we need first to state the real statement. So we have all needed tools. We have martingales, function calculus to define these kind of vector valued norm. For convergence, if we need convergence, because as an application, there is many theorem or convergence of martingale. So there is convergence in order, and sometimes we use the convergence, the unbounded order convergence. In fact, the almost sure convergence is the unbounded order convergence and not the order. The first result on convergence of martingale in Riesz space has been proven, and as a result, we show that the martingale is order convergent, which is a little stronger than the almost sure convergence. And I think it's not remarked before. So before the result says just it's almost surely convergence, but order convergence is a little stronger because we have a domination. A very useful result proved by Grobler says that order convergence and unbounded convergence for sequences, it's the same when we work in universal completion space. And we can show that for nets, it's not equivalent if the space has an infinite dimension. So it's not equivalent. They are two different notions, even if the space is universal completion. Okay, sometimes when we want to prove an inequality, we need another inequality. And it's the case here. This inequality, for the first time, because when things are well defined, it's easy, but before it, it's not easy. The first time I thought of the Burkholder inequality, it's because some discussion between Vladimir Trotsky and my student, and Trotsky said that he can see how to generalize this inequality. So we learn some papers on the Burkholder inequality, and we have this generalization. So this is not easy to prove also in the setting of Riesz space, and proofs are a little complicated. But here just I mentioned the crucial inequality here. And we have a duality formula. Recently, Bruce proves a nice result on Riesz representation for L2 of T. And then we can use the machinery of Hilbert space for L2 of T with of course some modification, but we have every not functional, but we have to define carefully what is function, what is the analogous of function in classical case in this setting, and can be represented as so the Riesz space said that every function on Hilbert space, so Hilbert space is equivalent to his isomorphic to his dual. Every function can be written as this. And a statement in Riesz space should be every something can be written like this, with some A here, but not every function. So Bruce and Kalush and Q managed to obtain a version, and it's somehow connected to this, because we can think now to duality in LP, some kind of reflexivity, etc. So this dual formula is used to prove this inequality and then to return to Burkholder inequality. You can. Okay, so this is the statement in Riesz space. So the quadratic variation is defined in a similar way, and then we have this inequality. So we can go further. The statement is very similar to the. This is a theorem that we can prove it using Burkholder inequality, or there is another direct and shorter proof in classical case obtained by Shaw, and we were able to develop a similar proof, but with many changement and generalization. There is a recent paper appeared in this direction. So there is a generalization of Kolmogorov maximal inequality and many others. What I want to say that even the proofs in Riesz space somehow follow the same ideas, but the nice thing that they oblige us to obtain another result in pure order space. For example, I can mention this one. If we have a sequence or even a net, but with sequence it's easier, such that, and we have a sequence of band projection satisfying this condition. So pk of xn converge to some yk in order for every k. And we have this condition that pk, we can take it increasing to identity, or even the supremum of pk is equal identity. Then the sequence xn converge in order to some x, but this convergence is in the universal completion. Why we very often we move to the universal completion? Because in the classical case, we can think of L1 of t as L1 space, but random variables live in L0, in fact. And even we start with a sequence in LP, we can, as a result, obtain something which lives in, which just random variables measurable. So sometimes even the condition are, we start by something in the space E, we leave space X, we leave X. So of course here, I said that order convergence and unbounded order convergence are equivalent. But some, if we start with the net here, we can obtain order convergence even we have a net of band projection. But if we start with the net here, what we get here is unbounded order convergence. And I think that this kind of result is needed, because in classical case, we can work almost surely, and after that we have a sequence of subsets with zero major, and then we take their union, etc. Here, what we have here with the Riesz space, there is nothing, there is no class, so nothing. We don't use the almost surely equality, and it's easier. Okay, next page. I think it's the last one. This one. Okay, thank you. what's below it's shukran in Arabic, but it doesn't appear. I'm sorry. How to?
So are the questions? Yeah, please, Yuri.
Thank you. I was wondering about generalizations of convex analysis. How much can be carried over to the Riesz space setting? Can you define subdifferentials? Is there duality theory?
Maybe, but just we develop some results needed to our inequality. There is some ideas using a component here, but there is some result on differentiability and derivative in Riesz space, but there is a lot of little quantity of theorems on this area. So as this theorem, just we prove what we needed, but of course we can think of something like this.
Some more questions or remarks? Okay, seems not the case, so let's thank you. So we have a coffee break now, and then we continue afterwards.